hitting the record button and I'm sharing my screen. There you go. All right, so today we are going to go over the last chapter of this class, the Stability of Slopes chapter. Typically, every year, we have to go over this chapter for 1 week. Unfortunately, it's a very important problem. The stability of slopes is a very important problem in soil mechanics class, but unfortunately, we only have a limited time to explain this problem to you. So basically, this week, I'm just going to give you a definition of the slope stability concept for soil slopes, because you are going to learn in a moment that the slopes can be in rock and also can be in soil. So this class is only concerned about the soil slopes. And I'm going to give you 1, 2, 3 alternatives for the stability analysis of rotational slides, and then maybe one alternative for the stability analysis of translational slides. And these are only basic information, but I'm going to say at the end of this chapter, if you would like to learn more about the stability of slopes, we have a 4th-year elective course specifically designed to teach you the stability of slopes. So if you are interested in this class, I'm going to refer you to a 4th-year soil mechanics class. All right, so let me start with the basic information. Then I'm going to show you how to proceed from here. First of all, I would like to introduce you the different types of slopes. We can classify the slopes based on their mechanism or based on their other properties. But the best way to classify the slopes is according to their reason. So I'm going to divide the slopes into 2 classes. One is the natural slopes, as you can see on the left-hand side. This is a natural hill, and you can see people settled here. This is a settlement residential area, and this is a slope failure, and this is a natural slope. So in natural slopes, the slope angle or the slope properties like slope height or any other slope geometry is not designed by the engineers. Okay, so the only thing that we can do for natural slopes is we can calculate their stability. Okay, and if their stability, if their factor of safety is not acceptable, if we think that the slope can fail, we can create or design some sort of measures to prevent that instability conditions. So this is not something that we designed. Okay, the only thing that we can do is to calculate the factor of safety against failure. The other alternative is man-made slopes, as you can see in the right-hand side. These man-made slopes can be there because of some cuts or excavations that we have performed. Okay, the faces of the earth dams have slopes, and any highway embankments that you can see all the way in your highways are slopes. So these slopes are created either by excavation of cuts or by fills and embankments. In that case, please remember the geometrical properties of the slope is designed by the engineer. The slope height is designed by the engineer. The slope angle is designed by the engineer. So during the preliminary design, the engineer can create a preliminary geometry and then calculate the factor of safety, and then play with the slopes geometry to get an acceptable factor of safety. So the first distinction between different types of slopes is their reason. The first option is natural slopes, and the other one is the man-made slopes. And for natural slopes, again, it's not designed by the engineer, so the engineer can only calculate the factor of safety and then take some preventive measures against failure. But for man-made slopes, the geometry is designed by the engineer. Therefore, the failure of a man-made slope is the responsibility of the engineer. All right? Now let me continue. In addition to the reason for the slope, I can group the slopes by their failure mechanism. Okay? This picture or this sketch gives you a simple geometry of the slope. Here is the slope's face. Okay? Here is the slope's top or head, and here is the slopes bottom or the toe, okay? And if the failure surface has a shape that's similar to a circle or an arc, then this is a rotational slip, and the failure surface has a circular shape. Sometimes, because of the different layers in the soil profile, we can still have a rotational slip, but the failure surface may not be a full circle or a full arc. In that case, we are going to call it a non-circular slip. So these two things are called rotational slips because the failure surface have a similar mechanisms, okay? And the feeling is that the failing soil is rotates while it fails. But sometimes the shape can be a full circle or a part of circle, sometimes maybe a little bit different than a circle, okay? These are typically happen in slopes with high slope angles, which are typically design or man-made slopes. Another option is called the translational slip. As you can see in translational slips, the slope angle is mild, okay? We have a mild slope angle, not very steep, but mild, okay? And the soft soils slip on a surface which is parallel to the ground surface, okay? In that case, we can say that this is a failure, it's something like a failure or a slide of a block, okay? Since the failure surface is not even close to a circle, it just, we don't see any rotation for the failing mass. We just see a translation. This is called the translational slip. We can say in general, the natural slopes, which are quite mild, may fall or fail with translational slip mechanisms, while the man-made slopes are generally more steep, and then we see a lot of rotational slips in man-made slopes. The compound slip is a combination of these two options. As you can see here, the slope angle is not very steep, but not very mild. And because of the layering of the profile, the slip starts like a rotational slip on the surface, but then it continues like a translational slip. So this is a combination of the rotational slip and the translational slip. That's why the name is called the compound slip. So if somebody asks you, can you please group your slopes according to the failure mechanism? The first thing you need to double check is the possible failure surface. If you think that the possible failure surface is close to a circle or an arc, you are probably facing with a rotational slip. If the possible failure surface is parallel to the ground surface, you are facing with a translational slip. If, because of the different layers of the soil profile, you see a combination of both, you can assume a compound slip. Even if the sketch is very, very simple, because it's just a sketch, in real life, these mechanisms are not very easy to understand before the slope fails. So I'm going to show you now two-dimensional pictures. Okay, here, this is a rotational slip. As you can see, the failure surface is an arc. However, when you look at the slope from outside, you are going to see some fractures on the ground, and then you are going to see some slumped or failed blocks. Okay, you are maybe not be able to see that rotational thing from the surface. Right? You are going to see just some failed soil surfaces and some cracks on the scarp of the slope. Here again, another example. As you can see, you see the scarp of the failure. This is again a rotational failure, but maybe not a full circle. Okay, as you can see, it affected a highway and cracked the highway from the middle. What we can see on the surface is very significant cracks. And just by looking at these cracks, we can define the failure surface through the failed block. Okay. Here at the bottom, you see a translational slip. As you can see, this time we have a mild slope, and then we can see a part of this soil body is slide over a surface which is parallel to the ground surface. So this is like a block mechanism. And this earth here acted like a block and slipped over a certain failure surface. And what we can see outside is just this failed surface. All right. So the slope stability analysis is one of the most complicated analyses in soil mechanics. However, unfortunately, we only had to spend maybe 1 week, 3-4 hours of lecture on this very complicated issue. The idea here is to just introduce you to the possibility of slope failure and then give you some idea on where to look for different type of slope failures. And then you will be all alone by yourself in your professional life. If you have to analyze a certain cases of slopes, you have to go into the details of slope failures. All right, any questions up to this point? Okay, so let me continue. Now that we understand the types of the slopes and the failure surfaces of the slopes, and we group them according to the shape of the failure mechanism, now let's think about the reasons or the causes of slopes. Okay. We can see that there are several important factors that cause an instability of the slope and that leads to failure. And one of the most easiest ones to understand is the gravitational forces. Just a moment, everybody. Let me close the door. All right, so let's discuss the gravitational forces first. Imagine now a force that we design, a slope that we design, a man-made slope. If the slope angle is too steep, then the gravitational forces may cause the slope to fail. In order to understand that, we need to calculate the resisting forces and the driving forces. If the resisting forces are smaller than the driving forces, the slope will fail. And for gravitational slope failure cases, the driving force is the weight of the slope itself. Okay, so if for a man-made slope, the geometry of the slope is not accurately calculated or correctly designed, then the gravity by itself can cause the slope to fail. So the first and the most important forces that we need to consider is the force that comes from the weight of the soil surface. Okay. Sometimes we can design the slope, okay, based on a slope angle and a slope height, and check for the factor of safety and make sure that we don't accept failure because the factor of safety is bigger than 1. Then the slope geometry can change, as you can see in this first picture, because of some erosion or some outside construction. Here, as you can see on this picture, this is the original slope, which is stable, and then by erosion, the angle of the slope changes. This is the new and more steeper slope. In that case, we can see slope failure. So it's a good idea to not to design the slopes just at this limit, but try to get a factor of safety way bigger than 1 to make sure, even if the slope angle of slope geometry changes for reasons that we don't know yet, the slope is still safe. Okay. Majority of the slope failures that we see has a cause that's related to the water. If we look at the pictures that we can see here, there are several reasons the water can create a slope failure. This is the face of an earth dam, okay? And this is the water that the dam holds. And because of the water, the soil here may erode, which is called scouring. And then this changes the slope geometry and causes a slope failure. Again, here, this is a dam or a water reservoir. And here is the water level for a high rain season. And this is the water level at a low rain season. The change of the water level, for some reason, is called the rapid drawdown. And imagine that this water is helping the slope to stay at place. If you draw down the water, that helping water force is removed, which creates a seepage force and then slope failure. Here at this picture, you should see that there is no water reservoir, but there is some rain, okay? And there are some cracks here that occurs because of tension forces. And the rainfall fills these cracks and the water seeps through this slope and causes failure. So one of the most important reasons for slope failure is related to seepage or reservoir water forces. Okay, that's why every year in the news, especially in the raining season, from the Black Sea area, we see a lot of landslides and a lot of slope failures. In Turkish, we call them heyelan. Okay? Her sene onlarca belki heyelan haberi duyuyoruz. Özellikle yağmurlu zaman. Okay? Another important reason for a slope failure may be the forces because of the earthquakes. Okay? Remember, the ground shaking is generally in the horizontal direction. Of course, there is ground shaking in the vertical direction as well, but the gravity is a very dominant force in the vertical direction. But typically, the stability of the slope in this direction is less than the stability in this direction. And when the earthquake forces changes the weight and forces acting on the failure surface, okay, you can see a lot of slope failures. Okay? And especially in highways, in highway embankments, the slope failures may close the highways for several hours, sometimes several days, which are important hours, especially after the earthquake, because all the equipment that is going to help with the damage should reach to the earthquake-prone area. However, when the highways are closed, the lifelines are closed. Therefore, it's very important to consider the earthquake forces also especially in earthquake-prone areas for slope stability analysis. Another reason for slope instability may be construction activities, okay? Sometimes you can design a slope, okay, and then keep excavating, and if this slope is not perfectly designed or just about to fail, as you keep excavating, you can see some slope failures. Sometimes this happens immediately after the slope is designed. Sometimes this happens 5 years after the slope is designed. So the engineer should be aware that even if I design the slope, 5 years later, somebody come here, change the geometry, my slope should still be safe after any excavation activity. As you can see, I give you a general pictures of failures of slopes, and you can see that there are several reasons that can contribute to slope instability. So one of the good things that we can do is we can use a large factor of safety at the beginning to make sure that rainfall activity, any activity related to seepage or earthquakes or any changes in the geometry doesn't really cause to failure because the initial factor of safety is quite high. Okay. All right. After we explain the different types of slopes, the different types of failure mechanisms, and different reasons for slope instability, now as an engineer, the only thing that we can do is to learn how to analyze the stability of the slopes. Okay. Here we should say that the thing that we are going to calculate in this chapter, or the parameter that defines the stability of a slope, is called factor of safety. Okay. So in this chapter, what we will calculate is called the factor of safety, Fs, and the factor of safety for slopes can be defined in 3 ways or 3 methods. The first and the most easiest one to understand is the force equilibrium method. Here, as you can see in the sketch, in force equilibrium methods, the first thing we are going to do is we are going to find the driving forces. What drives the slope to fail? And typically, the driving force is the weight of the failed surface. Okay. And then the second thing that we need to define is the resisting forces. The resisting forces are typically frictional forces, and one divided by the other, or the sum of resisting forces divided by the sum of driving forces is equal to the factor of safety. Okay, so there are some cases or some failure mechanisms where force equilibrium is used to define the factor of safety. For these cases, we are very lucky because most of the time it's really easy to calculate the resisting forces and the driving forces, and the factor of safety is 1 divided by the other. The other option that's fairly easy is called moment equilibrium. As again, you can see in the sketch, to be able to use a moment equilibrium, I need to have a point, and according to this point, or with respect to this point, I calculate the moment. As you can see in this picture, if the slope surface can be defined by a circle, then the center of the circle is a good place to calculate the moment. So we take the moment with respect to point O. Here, again, weight is the driving force, but I'm going to calculate the driving moment with the moment arm. And then here, as you can see, the shear strength or the friction is the resisting force. And I'm going to calculate the resisting moment with respect to point O, and 1 divided by the other is called the factor of safety. So these 2 options are similar. In the first option, we calculate the forces. In the second option, we calculate the forces and the moment arms, then convert them to moments. 1 divided by the other gives me the factor of safety. The last and the most popular method is called the limit equilibrium method. And in the limit equilibrium method, we divide the shear strength of the soil by the shear stress applied on the failure surface. And if the shear stress is smaller than the strength of the soil, the factor of safety is bigger than 1. So basically here, we do our calculations in terms of stresses, okay? Sometimes in total stresses, sometimes in effective stresses. But what we do is capacity by demand, and the capacity is defined by the shear strength of the soil, and here is the demand that comes from the forces. So whatever we use, everybody, the first thing is to understand what drives our slope to fail and what resists to the failure. After we understand these forces clearly, if I have to calculate the forces, easy. If I have to calculate the moments, easy. Or if I have to consider the stresses, that's also quite easy. All right? So in this class, we are going to teach you 4 methods. One will consider the factor of safety based on moments. The other one will consider the factor of safety based on forces. The last 2 ones are limit equilibrium methods, which will consider this in terms of effective stresses. But no matter what, the main idea behind it is very simple. All right? Any questions?
Hocam orada kırmızılı olan sum of resisting force divided sum of driving forces var ya hani.
Evet.
Force equilibrium.
Hı-hı.
Orada S subscript A var. O ne oluyordu?
S subscript A, oraları
Ya,
ben bunu bir sketch olarak gösterdim. Bu metotları ayrıca anlatacağım zaten. Hepsini.
tamam.
Tamam mı?
Tamam.
Burada önemli olan 3 farklı yöntem olduğunu, birinde force, birinde moment, diğerinde streslerin karşılaştırdığını anlamamız.
Peki dizayn yaparken hepsinin birden büyük olması gerekir mi?
Hayır, her bir slope çeşidi için, her bir failure mekanizmi için consider etmen gereken bu üçünden biri olacak.
Ha, tamam. Teşekkürler.
Mesela circular slope'larda moment equilibrium kullanacaksın. Moment equilibrium'da factor of safety hesaplayıp geçeceksin. Bazı case'lerde circular bile olsa moment equilibrium hesaplayamayacaksın. Limited equilibrium hesaplaman gerekecek. Tamamen mekanizmaya bağlı bir şey.
Okay, I understood.
All right. Any other questions for me? All right. So let me start with the first analysis, which is a very simple analysis, and it's called PU is equal to 0 analysis. Şimdi, eğer bu metodun adına PU eşittir 0 analizi deniyorsa, hemen sizin bana bu tip bir analizin hangi tip zeminlerde geçerli olabileceğini söylemeniz lazım.
Clay'ler mi hocam? Soft clay.
Killer mi, kumlar mı? Kimdir bu PU'su
Kil.
0 olan arkadaşlar?
Kil değil mi hocam?
Arkadaşımız kil diyor. Katılıyorum. Ama killer her koşulda PU'su 0 mıdır yoksa belli bir koşulda mı PU'su 0?
Saturated olması gerekiyor.
Değil hocam. Aynen.
Saturated oldu. Onu da cebine
Saturated.
koydum. 2 koşul daha olmalı. Kil oldu. Katılıyorum. Saturated clay katılıyorum. Hangi koşulda?
Normally consolidated.
Drained veya undrained. Seçimini yap.
Undrained.
Undrained. So this PU is equal to 0 analysis is applicable to clays, saturated clays, okay, where PU is equal to 0 and the shear strength is defined by CU only, okay? So we are going to start from the first one. And again, this first one is simple to understand, but only limited to a certain failure mechanism and a certain type of soil. Which type of soil? Clays, undrained conditions. Which type of mechanism? As you can see on this picture, a circular or rotational slope. So let me read the official sentence. The simplest circle analysis, which is called PU is equal to 0 analysis, is based on the assumption that a rigid but cylindrical or circular block will fail by rotation about its center, and that the shear strength along the failure surface is defined by the undrained shear strength C. So this sentence is trying to tell me that the failure surface is a circle, and I know the center of the circle, C, and I know the radius of the circle, R, and I know the angle theta, So I can calculate this failure surface's length. Okay. And along this failure surface, the shear strength is dominated by, or the shear strength is designed by or defined by the CU, because PU is equal to 0. Okay? Very good. At that particular case, if your soil is applicable to PU is equal to 0 analysis, then you are very lucky, because PU is equal to 0 analysis is a very simple analysis. Let me go step by step. In step number 1, first, I'm going to assume a trial circular failure surface. So basically, I'm going to assume this point C is right here. I'm going to assume the radius R, okay, and I'm going to assume the central angle theta. So this point's place, this radius, and this theta are all assumptions. This is a trial and error procedure. For every assumption, I'm going to calculate the factor of safety. Then I'm going to change this place of the center, change the radius, change the angle theta, and I'm going to calculate the factor of safety one more time. So I'm going to try and keep and change the trial failure mechanisms until I find the minimum factor of safety or maximum factor of safety. Imagine I tried 10 different surfaces and I get 10 different factor of safeties. One of them is the smallest one of them is the largest one. Which one is applicable? Or which one would you use in your design? The smallest factor of safety or the largest factor of safety? Bir kere de Türkçe soralım. Arkadaşlar, şunu söylemeye çalışıyorum. Bu analizin uygulaması oldukça kolay. Yalnız bu analizin bir kritik noktası var. Bu analizde C noktasının yeri. Failure surface'e giden o radius R uzunluğu. Ve theta açısı R assumption. C burada olsun diyoruz. R 10 metre olsun diyoruz. Theta 62 derece olsun diyoruz. Surface'ı çiziyoruz. Factor of safety hesaplıyoruz. 1.8 çıktı. Sonra C'yi değiştiriyorum. Bir daha hesaplıyorum. 1.7 çıktı. Sonra R'yi değiştiriyorum. Bir daha hesapladım. 2.2 çıktı. Her değiştirişimde farklı bir factor of safety bulacağım. Hangisini design'da kullanabilirim? Minimum mu, maksimum mu?
Maksimum.
Niçin maksimumu kullanıyorum?
Because if we are using the minimized side, we may get the risk, so it's not applicable.
Ben de
We can want to fail.
söyleyeceğim. Eğer sen 10 tane farklı factor of safety buldun, sonra bunlardan en büyüğünü kullandın. 2.2'dir bunun factor of safety dedin. Halbuki farklı bir trial surface sana farklı bir factor of safety verebilir. Tekrar söylüyorum. Bulmuş olduğum factor of safety'lerden hangisi gerçek factor of safety? Minimum mu?
En
Maksimum.
küçük olan.
Yani ben burada en küçüğü mü arıyorum, en büyüğü mü arıyorum?
En küçüğe göre projeyi yapmamız gerekiyor. En küçüğü sağlarsak diğerleri de sağlanmış olur.
Katılıyorum. Bence de öyle. Yani bu bir trial ve error meselesi. Ve biz burada değiştire değiştire failure surface'i bulabileceğimiz en küçük factor of safety'yi arıyoruz. Eğer bulabileceğimiz en küçük o factor of safety 1'e çok yakınsa bu slope herhangi bir sebeple fail edebilir. Yağmur yağar, crackların içine su yolar, fail edebilir. Efendime söyleyeyim, deprem gelir, fail edebilir. Demek ki bizim en küçük fail factor of safety'mizin bile 1'in bir hayli üzerinde olması gerekir. Değilse neyi değiştirebiliriz? What are the parameters that we can change in the design of the slope if the factor of safeties are too small? Everybody, what are the parameters that I can change in the slope? If the factor of safety that I find doesn't satisfy me, what can I change?
Angle,
Which one?
alpha.
The alpha angle. Your friend is suggesting, hocam, if the factor of safeties are too small, you can change the alpha angle. Do I reduce it or increase it?
Reducing.
We can reduce it. Okay. How about the h, the height of the slope? So there are typical geometrical parameters like the height of the slope and the angle of the slope that I can play with in my design. So the factor of safeties are more satisfactory in terms of performance. Okay. Did you understand the reason why I'm looking for the minimum factor of safety, everybody?
Hocam burada bir şey sorabilir miyim?
Tabii ki.
Mesela biz Factor of Safety'de resisting force, yani biz dedik ya biz 1'e yaklaşırsa, ama bizim için safe side'de olmamız daha iyi değil mi? Yani Factor of Safety'nin daha yüksek olması iyi değil mi? Neden minimize arıyoruz ki?
Factor of safety'nin daha yüksek olması daha iyi, doğru söylüyorsun. Sen buradan minimumu arıyorsun, diyorsun ki herhangi bir şekilde bana minimum factor of safety veren surface hangisi?
Ha, surface.
Bakıyorum,
Tamam.
aradın. Değiştirdin. Bulabildiğin en küçük factor of safety 1,5 çıktı. Diyorsun ki bu türlü koşulda 1,5'un üzerinde kalacağım ben. Eğer 1,5'tan memnun değilsem alfayı değiştirebilirim.
Anladım hocam. Teşekkürler.
Any other questions, everybody? All right, so step number 1 here in this analysis is we assume the trial circular failure plane. And we put the properties of this failure plane, like its center C, radius R, and angle theta. Then we are going to think, since we have a circular failure mechanism, and we know the center of this failure mechanism, let's think which of these alternatives, limit equilibrium, force equilibrium, or moment equilibrium, which one is suitable for us? And it's very, very straightforward because I can take the moments or calculate the moments with respect to the center. Here in this analysis, we are going to use the moment equilibrium out of these 3 alternatives. So here in PU is equal to 0 analysis, the factor of safety is equal to sum of resisting moments divided by the sum of driving moments. Now let's find which forces are driving forces, which forces are resisting forces. Who is going to try to take the slope down? The first candidate that we can find is its own weight. If the weight of the slope here is too heavy, then the slope will fail. So the first driving force is my weight. So what I need to do is I need to calculate the weight of the sliding mass, which is the area here that I show with my cursor, multiplied by the unit weight of the soil, will give me my weight. Okay. And in order to take moment with respect to point C, I need to calculate the moment arm D. To be able to calculate this moment arm correctly, I need to calculate the center of gravity of the sliding mass, because I'm going to put this weight on the center of gravity. So in order to use this method, I need to calculate from geometry the area of this failed surface, because when I multiply it with gamma, it's going to give me the weight. And then I need to calculate the center of gravity of this area, because I'm going to put W on the center of gravity and calculate the moment arm. So here D is the moment arm, and I'm taking the moment with respect to point C, so the driving moment is W times D. And I'm going to put them on the bottom of my equation, W times D. Can you follow me, everybody? Very good. Now, let's think, who is resisting to this force? Because the gravity wants to pull it down, somebody has to resist the gravitational force, try to hold the slope in place. And what tries to hold the slope in place is the shear strength of the soil, or the friction, no matter what you can call it. And since PU is equal to 0, this is only denoted by CU. And this CU times the length of the arc will give me the resisting force. All right. Hocam, is it easy to calculate the length of the arc? Yes, of course, because I know the radius. 2p times radius gives me the perimeter of the circle. Because I know theta over 360 will give me the length of the arc. So here, this L is your arc length. And again, you calculate it from the geometry. Cu times L is the force. Now I'm taking moment with respect to point C. What is the moment arm? What is the moment arm, everybody?
R.
R is my moment arm. So the resisting moments is equal to Cu undrained shear strength times the arc length that I calculate from geometry times the radius. Okay. Here, I can replace the arc length with P2PR divided times theta divided by 360. So if you can use this one, it's okay. If you see this donation, you are going to say, this is how they calculate the arc length. So here, the factor of safety is basically Cu times the arc length multiplied by the radius divided by weight of the soil times the moment arm. As you can see, the analysis is so simple. So the advantage of this analysis is it's very simple and almost everything can be calculated from the geometry. The downside of this analysis is this is only a trial surface. You need to consider 10s, 20, 30, 40, maybe 100 different trial surfaces to get the minimum factor of safety. Okay. The one important thing that we need to be careful about is the possibility of tension cracks. Okay. But I have to do that after the break. So let's take a break right here for 20 minutes and start at 2:50. Okay. I'm going to